Yeah, welcome to our course Aeroacoustics. Today we will mainly discuss how to transform our wave equation, the partial differential equation, for linear acoustics, or even then the Helmholtz equation, which is just the frequency partial differential equation. So we transform it into the frequency domain, solve and first transfer it to an integral formulation, and we will also look for different models for sources and then how we can solve it in this sense. So the main point, in order that you are able to transform a partial differential equation into an integral equation, is that you need Green's function. So in this sense, it is the following, that we have here, I just have tried to get this rid. So the main point is the Green's function, and what we will do here is that we will always have coordinates according to the observer and coordinates according to the source. So it is very similar, as we know from electrodynamics, when we compute the electromagnetic field at any position r, we also have to integrate over the sources in order to get the magnetic field at any observer position. And the main property of the Green's function is as follows, that as shown here, it solves the partial differential equation. So in our case, it solves the wave equation, and that for a delta pulse, as you can see here. And the delta pulse is concentrated at the source coordinate. And as you can see here, it clearly concerning time. So we have here this argument, t is equal to tau. So at time t equal to tau, this source is fired. And clearly it takes always some time when you're at the observer position x that you can hear the sound. We have the speed of the sound, which is in air about 340 meters, and therefore according to the distance and this velocity of the wave we have there, it takes this time. So the Green's function for this operator, for our so-called wave operator, is written down here, and perhaps you have already seen the Green's function for a Laplace operator. Yeah, this is exactly what we have is our Laplace operator, and that would be exactly this part here. Yeah? So you see that it is 1 over 4p distance between source and observer position, and due to the fact that we also have this part within the differential operator for our partial differential equation, for the wave equation, we have this so-called retarded time, as you can see here. So if you fire your pulse at tau equals 0, yeah, then you see this will be exactly the traveling time. And the traveling time is clearly the way from the source at position y to the observer at position x divided by c0, the speed of sound. Okay, now clearly what is our goal? Our goal clearly is to get a solution with a generic right-hand side, which is somehow a distributed source, perhaps somehow with some locality at some position, but clearly not only a delta function as we have assumed here in space and in time. Okay, and now the question is, can we use this Green's function now to get with such a source distribution an integral formulation which we have to evaluate to compute the pressure at our observer position X. And the main idea is, and that is important, so this is a very important part for us, is superposition. We all know it from electrodynamics, for example, but also from a lot of other courses. When we have a linear system, superposition is allowed. And when we go back, this operator here, yeah, our wave operator, second time derivative scaled with 1 over speed of sound squared, and second space derivative, according to the Laplacian, it is a linear operator, which means we can also now rewrite our source distribution as shown here in such a case that we make each point of the source distribution fixed according to our delta function in space and time. And then clearly we have to integrate, as you can see, over all the time where the sources are active and over all the space. And we not only restrict to where we have sources, we just go to the full R3, so the full spatial extension. And then the solution, clearly, since we know the solution of a delta source in space and time, and we can use superposition, we just use this and integrate then this source distribution we have clearly scaled with the Green's function, because the Green's function is the solution for such a delta pulse in space and time. And we integrate it over space and time. I clearly take here the integration with the y-coordinate, and we integrate over tau, which is the times where the individual sources being distributed are getting active. So we see this is now a reformulation. We have transformed, in this case, our partial differential equation into an integral equation. What we have not incorporated or discussed up to now, you just get a unique solution solving a partial differential equation when you also know exactly the boundary conditions. So on the whole surface, you need of your computational domain, you need the boundary condition and you need initial condition. However, let's say our space is infinite, and well, at the infinite space, there we clearly can assume that the acoustic pressure is 0 at infinity. So the boundary condition in this case is incorporated. What we here clearly can further explore are the properties we have, because when we now put in the Green's function, we not only have this decay by 1 over 4 pi and the distance between the observer position and the source position, we also have this additional delta function in. Yeah, and as you know, the special property of the delta function is the following, that it blends out the integral exactly at the position where the delta function is 0. We have to integrate over tau, so this delta function with the argument t minus tau minus distance observer to source position over our speed of sound is 0 if tau is equal to t minus this time the waves need to travel to the observer position, so the distance over c0. And that means we get rid of the time integration, and we get here then there should be, I don't know what has happened here, there should be clearly our acoustic pressure at position X and time t. And so you see, actually, what we have to do is we have to integrate over the whole space, which clearly we now could also restrict to just the source space where we have sources, because we integrate over the source coordinate y. But what is very important is we have now to evaluate our source distribution concerning time by this so-called retarded time. So we call this the retarded time, which is clear for us as engineers because we know the sound being generated at position y needs some time until it comes to the observer, which is at position x. Okay, so what we have assumed here is the Green's function for free field radiation. As I already have mentioned it in this sense, we assume we have an infinite space. We know that at infinity the pressure will be zero, so it is not allowed that we have any obstacles within our computational domain. So this is the main assumption we have done. However, it is general. If we know a Green's function for our setup, then just use this Green's function. And we will see that is a real challenging thing. And sometimes you just can compute such a Green's function by numerical methods. And then it is quite high, the computational demand of it. And then it will not give us such a big advantage. Okay. As you know, very often in acoustics, we are interested what is amplitude and phase, and we do the computation in the frequency domain. Anyway, we have mainly harmonic excitation at distinct frequencies. So we can also look and transform the Green's function to the frequency domain using the Fourier transformation. So with this HUT, it is now the Green's function, a function of space and frequency. We know this omega, perhaps I write always just is the angular frequency, it is 2 pi f. Yeah, and so just use your time domain Green's function and integrate it with this weighting here so that we get the transformation from the time domain to the frequency domain over the whole time t, from minus infinity to plus infinity. Now, we again clearly can use here our properties of the delta function. And we know the delta function plans out our integral exactly where the argument of the delta function is 0. So we have to put there at the exponent where we have minus j omega t, t to be equal the distance between observer position x and source position y divided by c0. And that has been done here, where we just introduce here the so-called, I should use here the other color, which we call, it's not here, the wave number. So the wave number, as you can see here, it is the angular frequency omega over c0, which we can also say it is proportional to the frequency. So high wave numbers means high frequencies. Okay, and that is the solution now. As you can see, we still have this amplitude decay by 1 over distance between source and observer, and we have this additional exponential function which defines the phase we have within our Green's function. Okay, so we see that we can, instead of solving the partial differential equation, we can also solve this integral formulation. And now we will have a look for different source distributions, or let's say models of source distribution, that makes sense, for which we get also then, at least for free field radiation, analytical solutions. And very often we have a so-called monopole source. A monopole is best modeled as the time derivative of a volume flow. Yeah? If you have a valve and this is opening and closing, then you will hear that noise, sound is generating when you open it, when you close it. And clearly you have, when opening it, you want to get some volume flow. When you have the according volume flow, then perhaps you can close it again. And what you see here, and that is very important, is it is the time derivative. Yeah? So in this sense, if we look now to such a volume flow, and so here is our volume flow over time, then according to the generated sound, it is not good that you immediately, what's going on here, that you immediately, perhaps I take here, no? Switch on and switch then when I have the amount of volume flow off, which means it would look like this. Yeah? You switch on here and you switch on. You close it at these times. Yeah. So from here to here in this sense, because you have a strong gradient with respect to time. So perhaps it is a better idea to use such switching on and off, which looks like this. So it is smoother. At the end, clearly the area when you integrate the volume flow over time should be the same, because you want to have some amount. But if you use, as you can see here, such a function, the green one, it is a more smooth function, and the derivative would be smaller, which means also your right-hand side, the source of the partial differential equation, will be smaller. So this is a simple approach, for example, to reduce the generated sound of such valves, for example, or any similar configuration. The next very important model for a source is a dipole. And the dipole, as you can see here, is defined by the spatial derivative of a force density on a surface. So you see it is the divergence of this force density, and there is, we should get this off. Yeah, you clearly can also define a point dipole, but I wanted to define here a general dipole. And that is, for example, when you consider you have an obstacle in a flow, then due to this obstacle, you will have on the surface forces acting from the flow on the surface. And this is then also generating sound, and it will be a kind of a dipole. So I give you an example here in this sense. So since we'll then clean it, we have here our obstacle, and you have here a flow. Then the flow has to go around. Perhaps it will here also generate, as you know, the so-called vortex street, and the sound radiation according to the forces. So perhaps I first take here to show you the forces are mainly here exerted on this part and on this part of the obstacle, and then the sound radiation will be like a dipole. So we will have sound radiation in this direction here and in this direction. So you see it is orthogonal to the direction of the flow. Yeah, so that would be such an example. Okay, so these are somehow modeled forces on surfaces, which will be also very important for us towards aeroacoustics. And we can also have a quadrupole source, a model for such a source. And this is now a second, as you can see here, a second spatial derivative of a tensor, in this sense, a tensor of second order. And this tensor, a 3x3 matrix in 3D, is computed, we will see then, according to the idea, the great idea of Lighthill, at least a simplification of the whole Lighthill tensor would be that this LIG is computed by the mean density VIVJ. Yeah? And the VIVJ are just the flow velocity components. And you see then when you do a first order derivative in space, you get the vector, and with a second order derivative, you get the scalar, because clearly our f has to be a scalar. So it is also, you can also rewrite it with the nabla operator as a second divergence on such a second order tensor. And that is a typical quadrupole. That would be a jet, for example, you have, and in free space, which we will discuss in detail. So these are three different models which very often can be used in order to get then simplified analytical solutions when we evaluate, and that is important, the integral formulation we just have found. Okay, do you have any questions concerning this idea with the Green's function and transforming the the partial differential equation, or wave equation, into an integral equation, which we also can transform and then get the solution, or at least the formulation, in the frequency domain. Concerning the Green's function, you already have seen it for the wave equation, or it was not within any other course you already have participated? I think you, in Toningenieur, you also have this course, Theoretical Acoustics. You have seen it there, or there was a discussion? You have to switch on the microphone, otherwise I don't understand you.
Do you hear me?
Yes.
So in Theoretical Acoustics, we had the Green's function, but also in Fundamentals of 3D Audio Technology.
Ah, okay, fine. Okay, so that is then for you not much new what I have told you.
I think recapitulation is a great way of
learning.
learning.
Yeah, of course. And I think it's also good to hear it from a different person. Everybody has somehow a different idea how to explain the topics.
Of course.
Okay. Yes, but that's good that you already have heard about the Green's function, and it is always easier to solve an integral formulation as to solve a partial differential equation. Analytically, especially when it comes to the analytical solution, perhaps we cannot solve it exactly, but that is very often not the most important case. The most important case is to get a good approximation, yeah, And that we will also see, for example, the far field approximation in acoustics, where we can transform spatial derivatives back to time derivatives, and the time derivative on any source is always easier as a spatial derivative. Okay, fine. So we can go on. And
Maybe another question.
Yes,
Can you hear me now?
Of course. Yes, I hear you.
Yeah.
Yes.
Yeah. No. This approach by Lytle, or can you give a example also for a quadrupole? Would it be if the flow of the obstacle more or less is turned in the flow, and then
no. For the quadrupole, it is really the following. You have, let's say, that was not good. I started. You have. We will discuss it, but we can have here. You have the nozzle,
okay.
and the flow is coming out of the nozzle. Yeah. Then you will have here a lot of vortices, but in order to apply this here, we have to cancel the nozzle. Yeah. Otherwise, it would be not correct. And that was somehow, then we will see, we will discuss this in detail when we go to the next topic, which will be aeroacoustics. That was necessary because at this time it was not possible to solve numerically for such a setup. The partial differential equation, so Lytle transformed into an integral formulation, and he was not able to take into account any obstacles, boundaries you have according to the nozzle, for example. Yeah. So he just said, I have a jet in a free ambient computational domain without any obstacles, and I just make some approximate solution with the integral formulation and get the scaling. How does the sound scale with the velocity coming out of the nozzle? And then we will see the great idea. Curl had also at this time some others, but Curl, I think, was the first. There's always some discussion if some Russian guys were faster, but in literature concerning publications, this was mainly driven by scientists from England, and it was clearly from aircraft industry. They wanted to get this jet noise you have in the air for the aircraft to be strongly reduced. And that could be at the end reduced by a bypass, yeah, that you have a bypass and not only a simple nozzle it was at this time. But that we will discuss, and then we will see how important it is to have some further ideas. But that we will also have in standard acoustics. So when you want to compute the acoustic sound due to a source like a loudspeaker or whatever, and that we will see today, yeah, that you can take into account the obstacles, even using the frequency functions, but then we have to know the pressure distribution on the obstacle. And that you mainly don't know. And so how to solve then this integral formulation, yeah? That we will see. That we will see. Okay. Yeah, fine. That's good questions. Okay. So first of all, before we come to a general formulation for any general setup, also including obstacles or including surfaces which are vibrating, we first want to discuss about the far field approximation. Far field approximation means, as shown here, we have here our sources, any source distribution, and therefore we see here the y-coordinate, and we are interested to get the pressure at any observer position, and in this sense far away from the sources, which means that the absolute value of the vector x is really large compared to the absolute value of any vector y going from the origin to any point within the source region as denoted here. Okay, we know we have this partial differential equation to be solved with any source distribution in our source region, we know we can also use here the integral formulation, and GF means the Green's function, and please notice we still restrict on the Green's function for free radiation. Anyway, if you have a Green's function, taking into account obstacles, whatever, within your computational domain, just use this special Green's function, and it is the same as you use the Green's function for free radiation. You just need this special Green's function, and you immediately have the partial differential equation written as an integral formulation, is shown here for the free fields Green's function. So we assume we have a source region. We want to compute the acoustic pressure in the far field, meaning it is far away from the sources, and let's look which simplifications we can do to still get accurate results. Okay, yes, and for this we have more or less two main terms. Perhaps I go back to show you the two main terms in red to consider. We once have this term here, which gives us the decay with 1 over distance. And don't forget, we also have here such a term in the argument of the source distribution. And in this case, it is a time shift between the original time t and the time which needs the wave to travel from the source to the observer. So we have to look now how we approximate these two terms, which are more or less similar, but the big difference is once it models the decay and once it models our retarded time. Now, the first one is the difference between the observer position and the source position, but it is the argument of the source. So we investigate the argument of the source, the so-called retarded time term. And here it is a good approximation that you not only simply use here just the distance from the origin to the observer, but use a Taylor expansion up to first order. So this is a Taylor first order. So you see, we approximate it now in this case, not only by the absolute value of x, but also the scalar product between the unit vector of the observer vector. The unit vector means because it is x over the absolute value of x, and project y on it. And this is exactly this part here. So for this retarded time for each source position, you evaluate in addition this term and approximate the difference between observer and source position by this term here. The second term, which is just a decaying term, well, here, which is standing in the denominator and which just scales the amplitude of the waves traveling to the observer, we can use this simple part and just neglect here the coordinates of the sources, and we just use the absolute value of the distance from the origin to the observer position. Now, if we put this in, we have one very important part now. Since we have used this approximation for the decay, we just have 1 over the absolute value of x. So it is not dependent anymore on the source coordinate y. we integrate on the source coordinate, and that is why this part is now out of the integral. And you see, you now just have to integrate over the source distribution, and you have now an approximated retarded time. Yeah? So this is an approximation. Instead of x minus y over c0, you have now just x over c0, and you correct this term by the scalar product between x and y over the absolute value of x and c0. Okay, which means, as we know from electrical engineering, this retarded time we can also interpret it as a phase difference. Yeah, so in the phase we have to be very careful to have a good approximation, and which means that at all the different points, yeah, within the source regions where we can have here some excitations, we take into account this additional term and not only simple approximate the difference between x and y just by x itself. Okay, so this was a very short part, but very importantly, I go back to this part, is that we really differ between the approximation we do in the argument of the source, so the argument of the source, and we do for the amplitude decaying term. Okay, so in this sense, we see that still for some source distribution, we will get good results. Clearly, we should be in the far field and not in the near field. You know, we differ between far and near field in acoustics. But you see, at least the evaluation should get easier now when we get out the decaying term out of the integral, and we now have just a corrected retarded time within the argument of the source distribution. Okay. So this is our far field approximation we have, and before we go on, we should also discuss what means compact in acoustics. That is also a very important thing, especially in aeroacoustics, where mainly our flow region is a restricted small region, and we are interested in the acoustic pressure, sound pressure level at a large distance, for example. Consider an airplane landing or takeoff. You are living nearby the airport, but the distances are always quite large, and you will not somehow have a flow in your garden. The flow will be around the airplane, so will be very restricted, but you can hear the noise even kilometers away. Yeah, and so the question is then again, for all the modeling of the different sound sources, what means compact and how perhaps we get a reduction in the complexity of our model. So what we consider here is an oscillating sphere. As you can see, it is just oscillating in x direction because the velocity amplitude has just a component in x direction, and this capital U changes, for example, according to a sine or cosine function with time. So we can model this as a point source, which means we restrict it, as you can see here, with the delta function. And since it is a dipole, yeah, you have here, according to this excitation, we have here the derivative with respect to x, y, and z. But since we just have a x1 component which corresponds to x, x2 would correspond to y, and x3 correspond to z in Cartesian coordinates, we just have a derivative with respect to x1. When we use the free fields Green's function, because we can do it, we have restricted it that the radius of the sphere is very small. That is why we have introduced this simple delta function. Then we have to take the derivative of this term here. You know, in order to come up from here to here, we have to integrate over the source distribution. But since the sources are located with this delta x function, you just blend out your space integral, which we have derived before, and you have here this retarded time t minus distance to the observer over C0, and we have divided it by the distance, the absolute value of x itself. Now, when we do some manipulations, which you find in the script, and we express now everything by the radial coordinate r, which is just the absolute, here, the absolute value of r, the radial coordinate, the absolute value of x. Then we can also rewrite the x1 component by r cosine of theta. So this is theta here. Then we get here a first term, and which is interesting, this first term, as you can see here, has a decay by 1 over r squared. And the second term has just a derivative, a scaling by 1 over r. So you have here this so-called near field, as we call it, term, and you have this far field term, because for being far away from the source, the first term will not contribute much because it scales with 1 over distance squared, and you can approximate everything by the second term, which just scales with 1 over r.
Excuse me.
Yes?
I have a question that is maybe a little bit trivial, but how can an oscillating sphere be modeled as a point dipole? Because I guess when a sphere is oscillating, it just changes its surface into all directions equally.
No. One moment. It is just oscillating in this way. Yeah. So just in x1 direction.
Okay. So the sphere is moving.
Yes. You can say it is. You can also model it that it is moving in x1 direction. Let's say by a sine function. Yeah. So it moves in minus x1 and then moves back to the origin and then to plus x1.
Okay, so
and clearly what we assume, I have perhaps not explicit, this radius r of the sphere we let go to 0. Yeah.
Okay. Yeah.
And that is somehow an approximation, clearly, but the farther you are away, the more this approximation is correct. Yeah.
Okay. So I imagine a small particle moving.
Yes,
like this.
yes, you could also say, but clearly we know if on the other hand, we know it is a model and it is not a reality, because if the sphere radius goes to 0, you have no oscillating surface. Yeah,
yes,
and we need an oscillating surface, otherwise we have no radiation. You are fully correct, but this is the assumption here. Yeah, and very often you then model a monopole or a dipole or even a quadrupole with the delta function to concentrate it in one point to get it easier. You see, we have this partial differential equation, try to solve it, but it's easier for us to solve it when we have the delta function. When you don't have the delta function, you have to integrate somehow over it. Yeah, we have, as you know, when I go back, we have to evaluate let's make it, Yeah, this is this. Yeah? We have to evaluate this integral here. But if we concentrate our source to a delta source, you know, then we have immediately the solution, because the delta source blends out the integral. Yeah, thank you. Very good question. I have not clearly described it. Okay, fine. So in this sense, now we have the following relation. We should, in this sense, have here the definition of the near field. And this is dominant at very small distances. Yeah. So when you are the observer, you are very near to this vibrating sphere, and you see what we have is that we have this relation here. When you have this relation, on the other hand, that can be also approximated, or not only approximate, it is proportional. So it's not approximate, it's proportional to the frequency over the speed of sound. And that is important because we know the higher the frequencies, the smaller our wavelengths lambda. So we can also say it is proportional to 1 over lambda. And I just rewrite it in this sense. We know that lambda is a constant value, speed of sound. Let's again concentrate to air, 340 meters per second. And then clearly we know it's a big difference if the frequency is 100 hertz or 10 kilohertz. The wavelengths gets smaller and smaller the higher the frequency is. So the simplest definition is clearly the distance of the observer is now really nearby the source, but nearby is not correct. Nearby would just mean that you don't consider at which frequencies you have the radiation of the sound. Therefore, this nearby is better to be expressed by the wavelengths. Yeah? So if the distance is small compared to the wavelengths, then you are in the near field. And we know, again, that this is equal to C0 over the frequency. So it is not only a question, where is the position of the observer? It's also a question at which frequency the sound is radiated. Now, in this case, when you are as near as defined here, that R is very small compared to the wavelengths, then it also means that the retarded time perhaps has no influence. Yeah, so you can forget the retarded time, because immediately you hear the sound because you are so near, and that helps us to transform the partial differential equation by the so-called Helmholtz number. This is the important way, and this Helmholtz number you now can see is something like 2 pi, which is just a constant. Important is a length scale L, that is any length scale, which will be a length scale according to your source over lambda. And if this is very small, now let's look at our partial differential equation. Since the time derivative here is scaled by the Helmholtz number to the square, and the Helmholtz number is very small, well, then you immediately could also neglect this term and could approximately write here just a 0, which means we have just a spatial derivative and we neglect the time derivative. And that is exactly what we have. When you have a Laplace equation, which is, for example, in electrostatics, yeah, then we have our free field Green's function by 1 over 4 pi distance between source and observer. We have no retarded time. The retarded time just comes in because we also have here this time derivative. But if for such cases you are in the near field and lambda is really large compared to the position where you are, then we can neglect the second time derivative because it is scaled with the Helmholtz number squared, and then we just have to solve for a Laplacian equation. And in the domain of fluid dynamics, this is somehow your incompressible potential flow. You describe an incompressible potential flow by the Laplacian of the scalar potential psi, which is called in acoustic, the acoustic scalar potential, and it is called in fluid dynamics the flow potential we have there. Incompressible, I just remember, incompressible means that the divergence of the what's going on here? The divergence of the velocity, incompressible velocity is 0. On the other hand, if we have a potential flow, we have no vorticity. And you know the vorticity is described by the curl of the flow. And therefore, this is always fulfilled when you express the velocity as the gradient of, I now take here just any potential psi. And if you substitute this in this equation, then we see it is the divergence of the gradient of psi is equal to 0. And that is actually the equation for a potential flow. And due to some boundary conditions where you know the normal component, for example, of the flow, you then get the distribution of such a potential flow. Important is just that we have such an equation at the end, and that means that we neglect the time derivative, and therefore you can neglect the retarded time, which also reflects in the Green's function. So the Green's function for this part here, when we write it down, would be the classical one, now just as a function of space. It is 1 over 4 pi x minus y, at least. I also write it here with the source coordinates y. And we don't have this additional retarded time. Okay, and that perhaps gives also some idea between a potential flow which changes over time and the acoustics, because in acoustics we always need some change in time, otherwise we cannot hear it. It has to alternate the physical quantity with respect to time, but we are in the near field and we can neglect the time derivative within our wave operator, and so it reduces to a classical Laplace operator, and it will be accurate enough also to describe the acoustic field in the near region of your computation. Okay, and that brings me now to our general formulation, as I have promised you. The general formulation means in this sense that, yeah, we want to transform our partial differential equation having also obstacles, yeah, and radiating surfaces. So here we have a radiating surface, and as you know, we need there the surface vibration of this elastic body, which could be the membrane of a loudspeaker. And we have always the continuity of the normal component, so n scalar product with the mechanical vibration, and the acoustic particle velocity has to be 0. And that means we need the normal component on the surface, which is vibrating. On the other hand, we can have just a scatterer. We assume that it is a sound hard body, but the question is now how to take this into account, such a sound hard body, so an obstacle within the radiating sound waves. And that will be the discussion, because when we know how to get from the partial differential equation to an integral form, we also have a general integral formulation for any problems we cope within acoustics. Okay, so for this, let's write down the wave equation here, as we know, with now the source position and time, y and tau. And you know, we have here the second time derivative, second space derivative, and also write down it with the free field. We even can use here a free field Green's function. We will see then at the end. Or you have the daylight Green's function, but let's for the moment assume you have a Green's function which fulfills this partial differential equation, where on the right hand side we have again a model for our excitation by the delta function in space and delta function in time. And now what we do is the following trick. We multiply the equation 2 by the pressure and the equation 1 by the Green's function. And very often you write the Green's function in this sense. As argument you have x and t, that is for the observer, and then you have this bar, and on the other hand you write y and tau, which is time and position for the sources. Okay, and when we subtract them, we have multiplied here in this sense. I write it here with the pressure, and this here we write with the Green's function. Then we get up to this long equation here, where we have not approximate anything, we just have extended the two equation and then subtracted. And now we will go over and integrate over source and space. And then clearly, just going back, you know, we have here the pressure. We have the delta function with respect to time, with respect to space. So when we integrate over space and time, it just plans out the time and space integral. That's why we directly have here on the left-hand side the pressure. And on the right-hand side, clearly, we have to integrate over tau and over y. And we have once this term here and once this term here, as we have reformulated these two equations and subtracted them. Okay, now what we can also see, and that is interesting, when you look at the first integrand, so this part here, what we have here, then you can rewrite it, and that's interesting, that you can rewrite it by this term. Let's have a look. We have here the second derivative, and now we just have a first order derivative, but we have put out this time derivative in front of these two terms. But this is equal because you have to apply the product rule. So for example, the first term here, so let's now put, okay, this, put this away. And now we look here for the first part here. Then what we get is, according to the product rule, let's first apply the time derivative on the pressure. So we have the time derivative of the pressure. Scaled with the Green's function. And then you have the pressure and you apply the time derivative on the second term. So you have the second time derivative, of the Green's function. Yeah. And when you also apply to this term, you see the following. We have a time derivative on the first term, which is the Green's function. And then when we apply it to the second term, we have just the Green's function second time derivative of the acoustic pressure. Okay, and that means that this mixing term cancels out. And then it's clear why the equality holds in our sense. Okay, so the result for the first term, you see why I do it, because now we can integrate here over time, because we have here this integrand, we have here the time derivative. So integrating over time gives us just the integrand itself to be evaluated at time equal tau equals 0 and tau equal t, which are the limits of our integral. Okay, and that we will see is 0. Why it is 0? So the first integrand is 0 at the lower limit, so at this limit here, because we specify that the pressure and the time derivative of the pressure is 0, because it's the time where we fire or we excite our sources, and so the waves cannot be at the observer position. For the second one, we have the causality condition. It's the same, because for any tau being smaller than t, our Green's function has to be 0, as well as the time derivative has to be 0 for such an evaluation. And therefore, it's nice that we have seen that this part gives no contribution. So the first part of our formulation is just 0. And it's due to the fact that the tau equals 0, we don't have any excitation at tau equal t, where tau is smaller than small t according to causality, because the waves need some time in order to approach the observer. This is also equal to 0. So the whole formulation now ends up in the second term, which is this term, where we have once the second space derivative of the Green's functions and the second space derivative of the pressure. And here we do the same trick. So we can rewrite it, and it's easily to be proven, as follows, that we have just this term and apply the space derivative on this term. And again, due to the product rule, you have to apply these mixing terms will cancel out, and just this will remain. So the equality is here really fulfilled. We do not do any approximation. And now you see clearly what we have here is the divergence, or let's say, of our term here. And that means we can use the divergence theorem, and instead of integrating over the volume, we now just integrate over the surface. And here just written out here with all the arguments of the pressure and the Green's function. And don't forget, we also have the normal vector to be taken into account. However, and now you see what is not easy here to get. We need here the pressure to be known on the surface, on this part, for example, if it is solid hard obstacle. And on the other hand, we need a derivative, and exactly due to this Ni, it's the normal derivative of the pressure, and there we have the relation to the vibrating velocity, which we will see in a minute. So we can solve it, but we just can solve it when we know all our boundary conditions. So for a radiating surface which is vibrating, we know that we have this relation here. We call it also the linearized momentum equation for acoustics. And as I have shown you before, the acoustic particle velocity, the normal component of the acoustic particle velocity is continuous to the normal component of the mechanical vibrating velocity of such a surface, which means by this relation we can rewrite it in this sense that we now get in this normal component, and it's actually not the velocity as we see, it's the acceleration. That is also a very important thing to realize, that for the sound generation, not the velocity of the vibrating membrane of a loudspeaker, for example, is important, is the main, but it is the acceleration, because we have the time derivative of Vn here and not Vn, the particle velocity itself for the mechanical vibration velocity of the surface. Okay, so when we now do, for example, a frequency domain formulation, we just apply a Fourier transformation, get rid of our time integral. Yeah, and that is what we now can see here, that we can compute the pressure at any observer position x, but we have to know, there is a mistake, sorry, I've just seen here, that should be gamma. We have to know on all the obstacles within our computational domain, we have to know what is the pressure there, or if it is a sound hard obstacle, or if it is something which is vibrating, we have to know the normal component of the vibration velocity of this surface. And this is just summarized here, so that exactly this acoustic pressure is mostly unknown on the scattering surface. Scattering surfaces are for us always surfaces where we have a solid body and we can neglect any surface vibration. So it is in this sense a scattering surface. On the other hand, we can have vibration surfaces which are vibrating. Simple example would be a loudspeaker, but could be any other surface, for example, the surface of an electric motor, which is vibrating and radiating sound. So we have to know the normal component of the surface vibration velocity, or a possibility clearly would be also you use a tailored Green's function, because this Green's function we have in here is the Green's function of free radiation. Yeah, but a tailored Green's function taking into account all your obstacles and vibrating bodies is in most cases not possible to compute analytically. A possibility you can use is the mirror principle. We know the mirror principle, especially from electrodynamics, for example, or theoretical electrical engineering. So it is the following: if this is, I write it here, sound hard, the floor is sound hard, you have here a radiating surface, you can take away this sound hard wall, but instead you have to include your image source, as you know, and then you get at the observer position the same acoustic pressure as you would solve the original problem of just having our radiating surface. So just having this radiated surface here and clearly the sound hard wall. Okay, that is clearly, as we know, also from electrical engineering, just for simple cases, you can find equivalent mirror sources and then can do this computation taking into account all the additional mirror sources. And since we have the property of linearity, we can use the superposition principle, so we can compute the arriving sound at the observer position for each source and then just superimposes, so means just adding up all the individual solutions. Okay, so if we don't find such a tailored Green's functions, we have to evaluate as shown here this integral. Yeah, and if you don't know at all our scattering surfaces the pressure, then this is an implicit formulation, as we call it, and you can also solve this. The more or less than standard numerical method would be the boundary element method. Yeah, so you also solve it numerically, but you have the big advantage, and I have to correct this here. This is gamma, that you just have to discretize all the surfaces within your computational domain, which could be scattering surfaces or vibrating surfaces, and then solve this numerically by the boundary element method. You don't have to discretize all the space in between, as it is the case for a finite element approach. Okay, do you have any questions concerning this now general formulation for computational domains with vibrating surfaces and with solid surfaces which are just scattering surfaces? Somebody of you already have done some numerical computation with a boundary element method? Okay, not. Okay, but you see, and that is important for me, that you see, now we don't have a volume integral, we have surface integrals. Yeah, and that's nice. But okay, if you don't know the pressure at this surface, well, then it is on the scattering surfaces, it is an implicit equation here, and you have to solve it numerically. And here clearly the best approach is to use a boundary element method, because you just have to solve for the surface integrals and you evaluate this numerically, and that results in the boundary element method. There are also clearly boundary element methods here. For the time domain, it's more involved, but also here at the TU Graz, we have some quite famous colleagues here, scientists also working to get boundary element methods in time domain. The standard approach is to solve it in the frequency domain. This is a standard numerical method you find in a lot of commercial softwares. And as I have told you, we are very often not interested to get the full acoustic solution in the whole computational domain. Very often we are just interested to have it at some monitoring points, and then you will be more efficient with the boundary element method as to solve with the finite element method, especially if you're interested in the acoustic pressure at a big distance, yeah, because you have to then discretize the whole volume up to this distance in order to get the solution with the finite element method. With the boundary element method, you're very efficient because you get then the solution, you just get the solution on the surfaces, but with the post-processing, you get them very efficiently at any point, and the point can be as far away as you want. You get it in a very short time, then the pressure also at far distances without doing discretizations, yeah, for this computational domain. We just discretize the surface. Okay. Do you have questions concerning this approach we have here, where we have now restricted to models concerning our sources? Next time we will discuss about aeroacoustics, and we will derive then the real aeroacoustic sources coming out of the flow. And then if we have the sources, we just apply the methods we have discussed today.
I have a question concerning
Yes.
the acoustic compactness.
Yes.
You mentioned the Helmholtz number there.
Yeah.
And the length scale L.
Yes.
And I was wondering if that length scale is a property of the source, because in
Yes,
other
of
lectures
course. Yes.
we learned the condition for a point source in 3D, that we are in the far field if the number k, the wave number, times the distance is bigger than 1. That was our far field condition.
That is also a good approximation, which you also get out here. One moment, and we go back. Here, you have it. Here you also have, as you see, the 1.
Yeah.
Yeah.
But the length scale is a measurement of the source.
Yes, it is a measurement of the source, the dimension of the source. Yeah.
Okay.
So we will then see for us, for example, in aeroacoustic, it could be the diameter of a vortex structure, for example. Okay. Yeah, because actually out of the vortices we get sound.
Okay.
Yeah, it is very good. I guess I have not mentioned it. This is really a length scale of the source.
Okay. Thank you.
Yeah.
Is it right that this term, what we see right now, is more or less k times r, because 2 pi divided by the wavelength is k, and so we should or we could write there k times l, and l is related to the r more or less.
Yes.
Yeah.
You can also write it. Yeah. And you will also find it that very often also they use just the wave number k.
Mm-hmm.
And we should have in mind k is direct proportional to the frequency. Yeah, we have just the factor there of the speed of sound, but we assume the speed of sound to be a constant. Yeah, so this is just the scaling, but doesn't change over frequency or over space. And yeah, one difference you will find in some books, sometimes you have the 2 pi included in the Helmholtz number, and sometimes they don't include it. Yeah, but that is the only difference you will find in the books. So since we derive here everything over omega, which is 2 pi the frequency, and you know when you do the Fourier transform, it is actually the angular frequency you have within the Fourier transform, you have this 2 pi. Yeah. But it is also just a constant shift you have, let's say, yeah, in the Helmholtz number, if you include the 2 pi or you don't include the 2 pi. Okay, then I think we can stop